Hello and welcome to the webinar of Würth Elektronik ISOs. My name is Eleni Stark and I will moderate the webinar today. We are very pleased that you took the time to participate in our webinar. Our speaker today is our product manager, Laurent Völkel. He will hold today's webinar and also answer your questions after it. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you can't ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via our chat function. You'll find the chat function in the webinar control panel. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 15 minutes in addition scheduled for this. If we are unable to answer all your questions within these 15 minutes, please email us at isos-webinar@we-online.com. We will try to answer all your questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to optimize our webinars. The link to the recording of today's webinar, as well as the presentation, will be sent to you in a separate email one day after the webinar. You can also watch the recording of today's webinar one day later on our website under the navigation point Webinars or on our Würth Elektronik YouTube channel. Now I'm giving directly to our speaker Laurent Völkel and I wish you an exciting webinar.
Hello everybody, my name is Laurent Völkel. I'm at Würth Elektronik Field Application Engineer and Business Development Manager for Energy Harvesting. Today I will talk about multilayer chip bead ferrites and about withstand, about the Inrush current, how to avoid to damage the components during the application. But first of all, I start a few words about talking about impedance, because when you use such products, you need to use that because of the impedance. You want to filter something. The impedance, actually, if somebody tells you that this ferrite bead have an impedance of 100 ohm, even they tell you at 100 megahertz, it's not so useful information, because the impedance himself, it's a calculated value about two components. One of the components, the impedance reactance, the XL, other one, the impedance losses, and the root mean square of both square are the impedance in fact. So you must know, if you want to filter something, you must act in the area where the losses are dominant. If you're just acting in a XL completely dominant area where almost no losses, you will have not a satisfaction of the filtering effect. You should always use ferrite core or material which are acting more resistive and less impedance reactive. If you take a look about the ferrite beads, you will find out there are many different ferrite beads, not only just over 10,000 products and part number. The part number already seems to be like a ID number or a phone number. There are differences between how they are manufactured. If you're looking for a standard ferrite bead, which are normally produced to be a wideband ferrite beads to cover as most as possible frequency, you will see that they will have a limitation in a high frequency, and you will need for a very high speed signal, if you want to filter the harmonics of that, something different like a standard wideband ferrite bead. We call them high speed ferrite bead or high frequency ferrite bead. The equivalent circuit of a ferrite bead is this LRC in parallel. The current take always the easiest way, the lowest resistance. Sometimes the resistance is through the L, sometimes the resistance is the lowest losses or lowest resistance and take this way, and sometimes because it's multi-layer and you reach by the layer above the layer, the higher capacity, the parasitic capacity, they will take the capacity way, because this is much more easier for that higher frequencies. Well, in the application normally it is like you're looking for a certain attenuation. You go to the EMC lab and you fail sometimes, and they congratulate sometime to you and tell you you have to go 40 dB down. Now, how to take this 40 dB information and calculate the impedance of the ferrite which you will need to use it. Well, it's not so simple. Even you know this formula of the insertion loss, you can use this logarithmic formula if you know two very specific values, and that is ZA and ZB. To use this formula, you need the source impedance and the load impedance. In a university, it's simple. Everything 50 ohm. In real life, it looks different. Well, to take out this ferrite impedance from the logarithmic, you can put that in the impedance formula like here. I draw it here in the exponential. But you still need these two different values, ZA and ZB. Without this information, you will not be able to calculate the right ferrite impedance. I saw that many new engineers and youngsters, when they have opportunity to filter something or they must do a work for a filter, first of all, they start to simulate. They start to simulate the source impedance, they start to simulate the load, and between the source and load, they put something like a LC filter and describe that it should be worked like that. Well, for the inductor, you can get from us replacement circuit, S parameter, spice model, LT spice model. Same for capacitor. You can simulate day long, but if you try to simulate your noise source, or even if you try to simulate your load, it will be not so trivial and not so simple. I would say, without having a PCB, without knowing exactly what is happening on your PCB, it is just wasting time. To start to use the right ferrite bead, I will start to use the insertion loss formula, but use practical values for source and load impedances. Like if you put ground planes together, sometimes you separe digital ground from analog ground. When you put them together, you should have a system impedance ZA, ZB, maximum 1-2 ohm. For the calculation, it's a good starting point. In reality, I will suggest try to keep that at milliohm. Milliohm is much better because you keep the low level of the impedances and you will not have a problem when you put too many capacitors, which they are always connected to ground. If you have power supplies distribution, VCC distribution, a value between 10-20 ohm, like a starting point for the calculation, is a quite reasonable point. If it's a buck converter, the output, you will see that even you will have less than 10 ohm system impedance for the source or for the load. If you have a video clock or data lines, 50 to 90, even to 110 ohm is very usual. Think about of USB port. A USB port have a data line impedance of about 90 to 110 ohm. It's a quite good starting point if you talk about data line filtering. If you want to filter some very long data lines, the impedance of these very long data lines could be even above 150 ohm. With this value, can start now to calculate your first ferrite bead impedance which you will need. How to find this out, which is 1 ohm and which is 10 ohm or 90 ohm? I put here an example of PCB. You can see this is a power supply. You can see here the ground planes. You can see here the RG45 connector. And on the back side of the PCB, you can see again the very thin lines. They are almost data lines. If you have this kind of big flat areas, that are mostly ground planes, and that should be very low impedance. If you have power supply, normally the tracks, it should be designed not so thin because you have to withstand for the current, and normally they are not so bright, like not so thin like data lines. Now I can show you inside of the ferrite bead how it looks a standard ferrite bead inside of the structure. This is a computer tomography picture of a 0805 size. On the left side, you can see the standard structure of a multi-layer chip-bit ferrites. There are some layers above each other like a sandwich. Left and right, you can see there are some pads. This is a soldering junction connection. And on the right side, you can see now the high frequency structure. They are not like a sandwich from top to the bottom. They are from pad to pad, like a harmonica. You can see there's a totally different layer structure. And because of that, of the high frequency area, you can put more layers inside and you can achieve in very high frequency some more impedance like with the standard structures. Additional, you have to take care about the maximum rated current which is passing through the ferrite beads. If you have to filter a power supply, we have here an example like a 2 amp ferrite bead. The 2 amp definition, it is when the component himself have a delta T temperature rise of 40 Kelvin, the maximum current should be not exceed by 2 amp. It means when you put 2 amp to the component and you have an ambient temperature of 20 degrees Celsius, on the component himself you will measure additional this 40 Kelvin. It means the component himself 20 plus 40, it will be 60 degrees Celsius hot. Take about this definition because this is only for a high current version available. If it's 500 milliamps or not a high current version, the temperature rise is just 20 Kelvin. Sometimes it could happen that you are using a 2 amp ferrite bead because you have a maximum current of your device of 1 amp and you think you use a 2 amp version, it could be more like enough. And your application could be an automotive application and you are supplying with a 12 volt battery, or it could be a very big capacity source as well. And you have a first input capacity. The say-in, it is 10 microfarad. This say-in have in an empty stage something like a ASR. This ASR and plus the DC resistance of the ferrite bead, if you apply the Ohm's law and you consider the 12 volt, it is 12 volt because the battery have a lot of energy, and you put the capacity like it is a short because until he will be charged it is just the ASR which is dominant. You may have a current through this ferrite beads which is very low 0.05 ohm DC resistance, a current of 22 amp. Well, this is just 11 times higher like the 2 amp which is normally admitted. Even if you will not destroy by the first shot, you will see that you will start something like a creeping process. Inside of the ferrite, something did happen which you don't see it, you don't feel it, you don't smell it, but it happens. You don't know how long the ferrite bead will survive. 3 hours, 3 days, 3 weeks, 3 months, or maybe 3 years. If it's more like 30 years, no problem, the warranty date is due. Well, how to see this? Sometimes it's very nice to see that in a laboratory when you have a real application with a 12 volt battery, and you can even smell it when the ferrite beads get too much current, and that's the rest of the ferrite bead. It's really sparking very nice. It smells like bad eggs, but it's destroyed the ferrite bead. It's just because of the inrush current. There are some nice pictures from our quality management guys where they did start to make some experience to make ferrite beads which are impulse current, inrush current tested, and we found many different applications where the ferrite are just exploding or cracking or melting away. Well, this is something which you're like a design engineer, you don't want to see in your PCB. Additional to the information that your ferrite bead should not exceed the maximum current, you have to take care because you have a maximum operating temperature of this component 125 degrees Celsius. It means if you apply the 100% current like 2 amp, you may have a temperature rise of 40 Kelvin. It means you can apply this product, you can use this product until a maximum ambient temperature of 85 degrees Celsius. Because if you put at 85 degrees Celsius the maximum current, which is 40 Kelvin, you may reach the 125 degrees Celsius at the component, and that's the maximum operating temperature. In case you want to apply at 100 degrees Celsius this component, to use this component, you must derate the current. You cannot apply anymore 100% of the maximum current. You should apply only just maximum 60% of his main maximum current. If not, you will overheat them and you will damage them. So you have to take a derating absolutely on this component because of the self-heating and because of the do not destroy the ferrites by too much temperature. Additionally, you have to take care that each ferrite bead is a completely closed magnetic field, and as soon you apply a DC bias current, you may have a saturation point. how much is this saturation point? I don't know if many designer or many manufacturer tell you. You can find all this information in our data sheets, or you will find all this on the website in the Red Expert software or in different simulation software. You can see here the ferrite bead on 0 DC BIOS load, like in every manufacturing qualify and specify in a data sheet, it is with 0 DC BIOS load. As soon you apply 600 milliamp, you may have a shift of the self-resonant frequency and you may have a decreasing of the impedance. At 3 amp, the maximum current of ferrite bead, you will see a lot of saturation of this ferrite bead. But honestly, if you will have 3 amp current, you may not have anymore the 50 ohm system impedance, because I never saw a data line with 50 ohm and 3 amp. Normally when you have 3 amp current, your system impedance is less than 10 ohm or less than 20 ohm. So in this case, because the system impedance is that low, you may have a compensation of the losses and you may have still a very good filtering effect. If you want to know exactly how much is that saturation point, if you are downloading the latest library from our website, you will find it even in the LTSpice 4, which is a free software from former Linear, today belongs to the Analog Devices. But you can download this LTSpice and you can choose this ferrite bead Z in bracelet I. This is a component where is the impedance on the dependency of the DC BIOS load. And if you don't change any parameter here on the simulation file, you may have exactly the measured values. If you change the step parameter from 0.5 amp to 0.25, you may have a mathematical interpolation. The same of the number of point. If you change the number of point or the frequency range, the rest is mathematical interpolation. But if you don't change, you can have exactly the values which happen in the ferrite bead during the DC BIOS load saturation. The next point is also important to see that if you make DC BIOS saturation, you may have in this decreasing of the impedance. When you are working with temperature range, again by minus 55 degrees Celsius, which is allowed to be used this component, you will see that the impedance is not so much influenced, just the maximum peak that will rise a little bit against the green line, which is at laboratory 25 degree maximum temperature. And at 125 degrees Celsius, you will see that it will be not influenced this area where the ferrite is linear. It is influenced just the maximum peak. At 160 degree, even out of the specs, you will see that it will drop just the peak, but not himself the impedance. Even if I'm zoomed that, you can see that changes are only on the maximum point. That's the resonant point which is influenced inside of the layer, that you will have a higher peak impedance on the minus degree or less so high peak impedance on the high temperature area. But inrush current, what means if I have a 100 or not 110 microfarad capacitor? You have a 10 microfarad capacitor, you have a nominal current actually from 2 amps, but when you switch on your device, this inrush will charge this capacity first, and now depends on your source, you may have sometime a very, very big impact. Yes, for this one, you should avoid such failure that the very thin silver layer in the multilayer exploding or just melting away. You can see that very nice in our computer tomography failure analysis. This is where the ferrite inside the layer is just melting away this ferrite, this silver layer, and that's happened when you have a pulse of 40 amp current for just 1 millisecond, and 1 millisecond is quite very short. But you can see what happened in the ferrite inside. It's actually degrading everything, and sometimes you may have even a connection. You cannot see from outside this, and you will have a connection here between these silver bulbs, but the ferrite is destroyed. It doesn't give you the same performance like should be. To avoid this, well, it's not so simple. Sometimes it's simple just to move the capacity on front of the chip bead ferrites and charge first capacity and then go to the rest of the electronics, but sometimes that's not possible. So you will need something which are withstanding this 36 amp peak, like here a 1000 microfarad capacitor, which can be even in the LT Spice very nice simulated. I would suggest for this area you should take you should take notice of the data sheet, and if you use a 300 milliamp current maximum current Ferrite bead, you will see that there are some notice here. It's not just a small letter. I can even make it a little bit bigger. It tells you should not use this component above this maximum rated current, else you will have a problem of destroying the ferrite or pre-destroy the ferrite. Move the capacitor front of the Ferrite bead. That's the one solution. If it's possible, that solves a lot of problem. If it's not solving this, or not a solution to solve just moving the capacitor, you can try something else. You can try to use this muscular power suppressor bead. We say them muscular bead because they are really massive and are really different manufacturing. And this one are manufactured in that way that we are using this layer in a totally different way. First of all, the layer thickness is much thicker like the standard value. And how we make this layer, it is always a secret of us, and we do that in one piece. So you don't have this soldering junction from layer to layer. The advantage of this new technology is that you will have an X-ray heat transfer and you will have a much lower DC resistance, absolutely. And this multilayer power suppression bead, they are really tested for pulse current. You can have a data sheet, or even you can simulate that in our Red Expert, the pulse length and the maximum current, how often can withstand this ferrite bead, these peaks. Normally you have a typical application like 2 amp, but this inrush area, it's your danger area. And all standard ferrites will break in this area. If you use the WE-MPSB ferrite beads, you will have this safety zone around. That could be 20 times higher like the normal typical specification. And it will definitely extend your lifetime of your product. In your datasheet, you will see that if you have something like a 10 amp maximum inrush current, you can use this 10 amp until several thousand times. If you have a 15 amp inrush current, maybe less than 50 times, because it will destroy it. If you have a inrush current which is only just 5 amp, you can use many 100,000 times and the ferrite will be never destroyed, or very late destroyed. This is always we say a TNT triangle. This triangle depends of the number of the repetition of the pulse length in milliseconds, and of course the ambient temperature. Additionally, you have an influence of the how long is the pulse pause from pulse to pulse, because for every pause of between pulse from 1 second to 5 seconds, it's a big difference of this triangle. It can be crucial sometimes how often happen this pulse, once per day, once per second, or once per 10 milliseconds, which is actually already not only our inrush current. You can see even in the datasheet of this MPSB that the DC resistance is quite very low, but again, you should not use this part component. Always be in a higher current like admitted. Do not exceed this current in continuous mode. Even you think, oh, that is by this DC resistance, I can put even 3 amp, much more like 3 amp, even 6 amp. It will be not a problem for the component. Please don't exceed that, because it will happen that again it will be destroyed. Here is a 50 ohm system, impedance with 0 DC bias load. This is the black line, and then when you start to put 1 amp, 2 amp, 3 amp, 4 amp, even to 5 amp, you can see that you will have even here, because of the physics, a decreasing of pre-saturation of the DC bias load of the magnetization of the core. If you want to avoid at all this multi-layer sensibility for inrush current, you can use the wired component. They are much bigger in size, of course, but they are safe for inrush because it's a copper wire. and the copper wire will be not destroyed by the inrush like a multilayer very thin few micron layer of silver. You can use this kind of different products, wired one. Like I told you, it is not a problem for inrush at all. I would recommend, if you use a ferrite bead, to use in combination with a C. You build a low pass filter, LC filter. Capacity should be a ceramic with low ASR, low ASL, high resonant frequency, of course. Even if you can use a P or T filter, but for the inductance, if you choose instead of a multilayer ferrite bead to use an inductor, check the Q factor of the inductor. The quality factor of the inductor should be low as possible, because in the filter it's very important that the Q factor is very low. If the Q factor is too high, you may have a ringing of the filter as well. And please pay attention of the self-resonant frequency of the used components to not build oscillators. This is a typical application for a buck converter. You have an input capacity. According to the switching frequency, you can calculate the third harmonic, put an inductor. Be aware that this inductor should be not too big, because it should be charged in time, the input capacity. So it must be correlated to the input capacity value. And if you want to have a very, very good conductor emission for a buck converter, you should always filter the input. I would suggest to put additional ceramic capacity, 220 pico to 1 nano, and the ferrite bead between 100 to 300 ohm. Don't use a 3 kilo ohm, the most powerful one, just only because of 3 kilo ohm. Because you do not need 3 kilo ohm here, and the 3 kilo ohm have too many layers, and you may have a peak of 3 kilo ohm but not a nice bandwidth coverage of full frequencies. I will use a 1 to 300 ohm, which is quite enough. If you make your layout, please don't use that in the left side, use in the right side. After you place the capacity, put the via to the ground plate very close to the pad. Even if you use 2 vias, it's much more welcome, because one single via have 0.5 nanohenry inductance. Keep the tracks short as possible, because they are parasitic inductive. Additional, by soldering, you should take away that if you make too big junction for the soldering pad, you may have this tombstone effect. If you take the recommendation from our ferrite beads, normally it will not happen any tombstone effect by applying the standard JEDEC soldering profile. Additional, you have to take care for the mechanical cracks, because if you place very close the ferrite bead to the edge of the PCB, it may be destroyed by the mechanical stress, and you will have some cracks on the surface, only because they are very, very hard like ceramics. It's very simple and similar like ceramic capacitor. Avoid to apply to them stretching or mechanical stress. Even when you are using PCBs in a very big PCBs, apply the ferrite bead not on the length side, put them place them on the PCB on the shorter size. And when you have such kind of breaking lines, you should place that like recommended on the short side, not on the length side, because else you may have a damage. By pick and place, again, if you have PCBs which are bending, put some supporting pin above, below the PCB to have a good mechanical fixing, to not destroy the PCB, the ferrite beads during the pick and place. More information you can find in these different books. We have this trilogy of magnetics, or LT-SPICE, connectors, power module, ABC of transformers. You can find all this book on our website, or by our distributor, official distributor, or just on a website from Würth Elektronik. Just ask our sales guys for that. It will be not a problem to get this book for free. If you have questions, please put your question now in this chat or questionnaire, and I will try my best to answer to them. The most message what I want to tell you, it is there is always a solution. Never give up. It's always a solution. Just maybe sometimes you don't see it. We try our best to help you. We try to give you support with our worldwide field application engineers, and try to give you some information additional which is not sometimes written in the datasheet. If you want to keep in touch with me, I'm also on Twitter and also in LinkedIn, or we have this landing page at Würth Elektronik, or even to contact me directly by the email address. Now I will try to see which question have been advised? Okay, question. Okay, one question have been done, and somebody asked, why is the storage temperature in the data sheet minus 20 degree plus 60 degree, and why is the operating temperature minus 55 plus 125 degree? Well, the answer is very simple. When we deliver our chip bit ferrites in tape and reel, believe me, even if you have a warehouse in the deepest north point of Siberia, you should have some heating there and should not keep that at minus 50 degrees Celsius, because when you want to pick and place at minus 50 degrees Celsius, this component in the tape and reel, the plastic could break very easy because it's very cold. Above 60 degrees Celsius, honestly, even if you are in deep Sahara, in somewhere where you keep your warehouse and want to make a pick and place, a plastic above the 60 degrees Celsius will be again a problem. And if you put the tape and reel at 120 degrees Celsius into the oven, you will see that you can't solder anymore because they are melting together. Well, this is the only one request, that if you pick and place this component on the board, doesn't matter if you power or not power the ferrite bead, they have already the operating time started. So you can use them between minus 55 and 125 degrees. You can store them even after it is soldered, but not in tape and reel. That will be a problem. Another question just coming in. How to choose the bead resonant frequency? Well, in every data sheet, we are showing the impedance versus frequency curve, and the maximum peak is the resonant point. Additional, I can show something, maybe some simple, because if you go to the Red Expert area and you look on this Red Expert filter design tools, you can put your mouse on these pulse ferrite beads, and you can see here by the impedance, you choose just one of them, you can see here the maximum, this one, you can see here the pulse. No, that was the wrong one. So right, ferrite for PCBs assembler, that was the wrong one. Ferrite for filter design, impedance of PCB ferrites here. Now you can see here on this, the maximum, it is here where the ferrite have the resonant point. So this is the self-resonant point of the component. Definitely, I would suggest to not use this ferrite because have a high impedance at 400 megahertz, have 220, 240 ohm. I will use always a ferrite in this area where the ferrite is start to increasing before the resonant point. Always use before the resonant point. Now, if you have an application for the inrush current and you want to know exactly how much pulse for this ferrite bead can be applied, then you can go to this MPSB series, and you can see here with this ferrite bead, if I apply here pulse of the current, I can specify here some current, some length, how long should be this maximum pulse on that. You will see pulse here. You will see that at 20 amp pulse, a single pulse, which have 1 millisecond, you can apply maybe 1000 pulse at maximum 5 amp, and this ferrite bead will withstand without any problem. So you can see here the maximum time and the maximum current which this ferrite can be admit. If you have 100 amp, you cannot admit that for 5 milliseconds, but for a few microseconds it will be not a problem. Again, number of pulls of 50 amp, if you have 50 amp inrush current, you can apply this 50 amp maybe only 265,000 times. If your inrush current is less than 20 amp, you can apply that for many 100,000 times. It will be no damage. And this is from different ferrite bead construction. You can even compare them at the different points. All this information, it is given in the in this Red Expert in bash rate values. So let me check some other questions. Again, somebody asked and mentioned that 100 megahertz or 200 megahertz is far away from DC-DC converter frequency. Well, it's very funny that even if you have a DC-DC converter which is running at maybe 1 to maximum 5 megahertz, even today we have DC-DC converter which is running already at 100 megahertz, you will be very wondered in the EMC laboratory when they measure the radiated emission that above, far away from this 100 megahertz area, you may have some very interesting resonant point, and this very fast rise time on your MOSFET, especially these new GaNs. If you use them, even you have a switching frequency a few kilohertz, you will see that you will have problem in several hundreds of megahertz just because of the DC-DC converter. And that will happen maybe not so often, but when it's happened, then you have a possibility to use that kind of ferrite beads for that. Okay, I see some other question which I will respond them by email later on. So I hope you enjoy it. I don't want to exceed too much the time. And if you have any question, just place and I will answer it by email. I hope you enjoy it, and I wish you a nice day for everybody, and say bye-bye.